there are two types of energy that we perform calculations on. There's kinetic. Let me get that into black. We have kinetic energy, and we have potential energy, but there's only really two of these that we do calculations on. We could do calculations on others if we were just given numbers, but we have our gravitational potential energy, the energy something has because of its position relative to normally the Earth, and we have elastic potential energy, energy stored in a stretched object. Now, it's important when you're writing answers that you say elastic potential energy, not just potential, not just energy, of course, because energy doesn't tell us very much. Potential energy tells us more, but not enough, because there's two kinds of potential energy we do calculations on. There's many more, of course. We also have nuclear, for example, and chemical, for example. So there are other answers you could give in terms of what kind of potential energy we're talking about. But in terms of calculations, we have formulae for these two, and we have a formula for that one. And so it's those that we will do calculations on. So let's look at those then in turn. Let's look at kinetic energy first. This is, of course, energy due to motion. Easy enough to remember if you think, if something's going to hit me, what would affect the amount of pain it causes? Well, if something is traveling faster, the velocity or speed will affect how much it hurts. And of course, if you're hit by a table tennis ball traveling at 3 meters per second, and you're hit by a cannonball traveling at 3 meters per second, the cannonball, because it has more mass, even if it has the same size, same volume, the cannonball will hurt more. So the energy that's involved depends on the velocity and the mass. It's actually the magnitude of the velocity we care about here, so the value of the speed is good. So putting that into our formula then, we've got the kinetic energy, I'm going to call that E subscript K for kinetic, is a half times the mass times the speed or the magnitude of the velocity squared. And let's see if I can put a nice box around that. A box is what I wanted. There we go. And of course, the energy, all forms of energy measured in joules. Lowercase word or capital J. So that's kinetic energy. Let's then look at potential. Two kinds of potential, gravitational and elastic. Gravitational energy, Well, if you consider the ground level, sorry, I meant to do that. So if you consider ground level there, and let's take ourselves an object which we have raised from ground level, and let's say that object has been raised a height h, so let's say we have mass m kilograms, raised a height, let's call it delta H, a change in height. And let's say that the gravity is, that's in kilograms of course, that's in meters, gravity is G, meters per second squared, or newtons per kilogram. Same thing. So the gravitational potential energy then, or the change in gravitational potential energy, is mass times gravity, acceleration due to, times change in height. Or EP, or the change in EP, is mass times gravity times change in height. And again, let's see if I can put a nice box around that. There we go. So that's our gravitational potential energy formula. Over here then we have ourselves elastic potential energy. So this is a graph of extension against force for a spring. You've done this experiment before. It gave us Hooke's law, you'll recall. Which was that the force is some constant, the spring constant, times the extension. Now, you'll also remember that work and energy are the same thing. You'll remember that work is the ability, energy is the ability to do work, and work is done, energy is converted, and the amount of work done is the amount of energy converted. You'll also remember that work is force times distance moved along the line of action of the force. I won't write all that down, but that's what I would write. So, if we multiplied the force by the distance moved along the line of action of the force, we'd do force times extension. But if we were to take this value, F, and this value, E, If we multiplied F by E, we would get the whole of this area, this rectangle. But actually, the energy stored in the spring isn't the whole of this. It's just this bit. So it is the area of the triangle. So our elastic potential energy would be a half times the base times the height. Base, height. So there we have an expression for the elastic potential energy. And of course, we could then substitute K times E in here, and we'd end up with our elastic potential energy is a half F times E. If we put KE in there, then we'd get a half KE squared. So either of those two expressions is good for elastic potential energy.